We will continue with Professor Shinji Watanabe. So, I mean, he probably doesn't need any introduction, but I'll give him one anyways. So, Shinji Watanabe is an associate professor at Carnegie Mellon University in Pittsburgh. He received his undergrad, master's, and PhD from Waseda University, Tokyo, Japan. Before CMU, he was at in NTT, Merrill, and Johns Hopkins University. His research interests include ASR, speech enhancement, spoken language understanding, and machine learning, in general, machine learning and language processing. He has published over 400 papers in journals, conferences, all over everything. And he received the Best Paper Award in ASRU in 2019. He is a senior area editor in IEEE TASL, and many things. He's an IEEE and ISCA fellow, and we are really, very privileged and honored to have him here today. And he'll talk about building explainable foundation models for speech.
Okay, Jim. Thank you so much. Today, as Jim mentioned, I am explaining about some of our group's effort of how we. Is that working? That is better. Okay. How we try to kind of build a speech foundation model, and through this kind of the struggling, we actually found that explainability is a very important component. So with this kind of the presentation occasion, I just want to explain our the effort in this direction. So first, I just want to mention some of the introduction. So many people may also have this kind of the thinking. So first, the science was actually starting from the alchemy, and then now it becomes science that we know. And there are a lot of difference from the alchemy to science, but one of the most important critical change in the science to the alchemy, for me personally, is because of the reproducibility. Reproducibility is a quite important component when we try to perform the science. And this talk, I will also more focus on this reproducibility. But I just want to mention that the reproducibility is important, but at the same time, I also understand that the reproducibility can be sometimes lower the priority due to your constraint. So my talk is just want to kind of provide you that this kind of the way of the making the emphasis of the reproducibility is a complementary effort to the people, especially in the industry, that had to have a more focus in the other direction. So anyway, I will start to explain about this the reproducibility problem. Speech, audio, and of course the all other areas. Now the foundation model becomes quite kind of important and popular. And we actually have a lot of effort for the foundation models reproduction. Early 2020, we started to have actually some of the foundation models based on Web 2, Web 2, and so on. And then we started to also reproduce some of the self-supervised learning model, especially Hubert. And again, this is not only our work. We actually had a lot of the help from the Meta, and then tried, but it's actually failed, mostly due to the kind of lack of the experience. And we still continue this kind of ways to how to reproduce it. And Google actually proposed the best RQ. And then again, we reached out to the people in Google, and we tried to kind of reproduce the best RQ in our the code base. Again, it was not a good success due to the same reason. We didn't have enough information about how to make it compared with a big industry and so on. And later, OpenAI Whisper came out. And then last year, we finally started to actually reproduce the very large model. I mean, currently it's not very large, but at that time large, Hubert large, that we actually reproduced it with an academic computing scale. And last year at ICASP satellite workshop in the other one, I actually explained this one. And then the rest of the last year and this year, we actually started to reproduce the OpenAI Whisper. And having some kind of a result in the initial part, and then we further kind of accelerate this project with make it faster and better. And more especially, importantly, with this kind of process, explainability is actually quite important. So let me talk about today's agenda. The first part is the introduction of our effort to the reproducing OpenAI Whisper. And then we actually found a lot of the findings, lot of kind of important findings. Based on this finding, the second part is focusing on improving the model. By the way, today's talk, compared with the other keynote speaker or invited speaker, mine is a little bit different style because more focus on the reproducibility of the large models. But I also have several kind of study of how to make the neural network to be more interpretable based on some kind of forcing the structure and so on. If you guys are also interested in this direction, please also check some of my previous talk, especially the one I had in the same 2022, which is about explainable neural network for the conversational speech analysis and understanding. But anyway, today I will talk about the reproduction side. Okay, so let's start about the motivation of this kind of work. So first, I really kind of excited about the OpenAI Whisper, especially they are very great about prompting. Before that, we actually couldn't make a good prompting in speech models. But after the OpenAI Whisper, we can make it quite kind of the rich prompting and a lot of application we can produce. Very cool. However, at the same time, not only me, many people actually concerned about Whisper in the open science perspectives. For example, we don't know the training data. They actually didn't release it. Again, I don't criticize it. It's based on the company's restriction, we definitely should have such kind of issues. And I fully understand it. But as a fact, we don't know the training data. We don't know how they train the model and so on. And then it's actually making it quite kind of difficult to understand the behavior of the Whisper. So for example, these are actually a little bit famous, so people may know. But anyway, Whisper, when we throw the kind of silence, completely silence, they actually say thank you. They actually, given the silence, recognize it as a thank you. I don't know what's happening. This is because of their training data, their way of training is quite kind of a secret. So we couldn't fully understand what's happening inside. So we actually started to make we started to think about the reproducing the Whisper based on this kind of issue. Another kind of important part is the fairness and the biases issue. Again, we don't know the training data. So Whisper may have, actually many people reporting, have some kind of fairness and biases issues, especially some particular other group of the speakers, they can well recognize, and the others not. It generally happens, but since they don't kind of reveal the training data, so we cannot do anything more than that, than just fine tuning. So due to this kind of various kind of the problem, although Whisper is very kind of cool, but maybe we should try to reproduce it so that we can make this kind of our community healthy. So that is our kind of motivation of working on the reproducing Whisper in academia. Okay, so now I move to the what is the Whisper? So some of people here may know and some people may not know. So I will recap some of the kind of unique part of this model. So first, Whisper is based on very large amount of training data. Their initial version is 680,000, and now they are actually using 3 to 4 million hours of training data. And I would say that if we have the order of 10,000 hours, we can make a very good product system. And 100,000, even we can make it more. So in this sense, this training data, even in the industrial scale, very, very large. With not just training data is very large, Whisper also has a various kind of function, like a language identification, the speech translation support, timestamp prediction. Also, they are based on the chunk-based approaches, not like a sentence-based approaches. This is very unique and different. So our goal is, again, we try to reproduce Whisper based on the open source toolkit. We actually maintain the toolkit called ESPNet, and we use this one and try to reproduce the Whisper. Data, we completely using the public data. Well, it's depend on the definition of the public, but we using the LDC data and some of the open data. And we all disclose the list of the data. In addition, we also disclose all kind of a training procedure, data preparation, detailed know-how, model checkpoint, source code. And then we actually are building the speech foundation model. By the way, this one, we name it OWSM, Open Whisper Style Speech Model. And please pronounce it awesome. Okay, so let me discuss about some difference. Of course, we cannot fully reproduce because our computational the resources and so on. But anyway, we target it to the Whisper medium model. And then we gradually improving the model size, increasing the model size and the amount of data, and then make it in the currently the V3. That is a kind of our the previously successful model. And then I will also explain about some of the extensions later. And but anyway, B1 to B2, B1 to B3, there are some changes in the model size, but mostly we changed the amount of training data. First, starting some of the training data, and if you are familiar with speech the area, you may actually know many of the data here, right? I really kind of appreciate that, by the way, the community, that we actually have 180,000 of the training data we can collect by using the people's effort and putting in the LDC or putting in the web, and then we can actually make such kind of large amount of training data. And then what kind of model do we use? We actually using almost exactly same as the Whisper. Again, this is a reproduction project. We want to kind of make it improve in some stages, but this work, we stick to the reproduction. So we try to kind of use the same architecture, same way of training data read from their paper as much as possible. But there are some minor changes, especially try to kind of make it faster, like using the more downsampling, using the CTC loss to make it faster convergence, and so on. In addition to this kind of effort of making some training tools, actually after we learned the training, we encountered a lot of other problems. And then we actually had a lot of engineering effort to finally make this training work. For example, the one of the kind of important part is that Whisper is using the 30-second chunk instead of the sentence. So we actually change completely all kind of data preparation process of our existing training data pipeline. And then there are several other lot of the kind of issues I encountered, like, the data is anyway very big, so we cannot actually have a list anymore. Or the cleaning is also very difficult. And this is actually now fixed, but it used to be always there are some issues in the file server. And then we have to actually manually restart the models and so on. That is actually also very painful. And people are also maybe very kind of curious about the budget. And I'm also happy to disclose, and I'm also happy to, share my experience so that if you guys want to try, let's try to do that together based on my experience. So first, we used over 120,000 GPU hours only for this project. And if we convert this one to the AWS, it actually goes to the amount of 100,000 or even more. But by the way, I will explain later, I actually don't use AWS. And some people may not use a kind of GPU credit based. They may all have their own kind of the GPU resources and have never counted it. So I can give you the kind of sense. Usually, if we have 10,000 GPU hours, we can write a very good paper. We can write many kind of, we can do the many kind of experiments, ablation study, large scale experiment, and then writing the paper. So this 120 corresponding to 12 the paper effort actually. And then this is actually quite limited trial. We just have again the B1, B2, B3 only 3 times. And every kind of the model building, we only see the model, entire model 2 or 3 times only. We don't have so many kind of epochs due to the kind of quite expensive training data. And another issue that I actually got several kind of point for this, and I have to admit that I have to be more serious about it, which is the carbon footprint. So we really seriously thinking about this the carbon footprint after this project and so on. But anyway, this is more like a training cost issue. And by the way, I will pick up several other issue and then we'll summarize it later. Then I mentioned that I didn't use AWS or some other money. I actually didn't spend money for this project. How did I get such a GPU resource? We actually get help from the Supercomputing Center in US. This is actually supported by National Science Foundation. And the NSF are actually supporting several supercomputing centers, one in the Pittsburgh, one in the Illinois, and there are several others in the various states and so on. Also, that we got some kind of Amazon, the AWS, the research award, and then use some kind of AWS credit for the initial trial. But I'm mostly using this two supercomputing center. And again, I didn't spend my account. Instead, I'm using 15 pages of the long proposal. So again, I'm happy to share my experience of how to apply this kind of the supercomputing center and how to get the large GPU resources and so on. I'm sure that the other countries also have a similar the structure and so on. So please do not hesitate this part, and please ask me anything about the computing resources and so on. Okay, so let me explain about the some of the explanation experimental result now. So since the first part is reproduction, so I focus on the two part. One is the performance, of course, and the other is the functionality. Whisper has a lot of functionality. And to see whether this functionality we retain or not, it's also kind of important. So first, let's check the performance of the English ASR. And it's actually the awesome is doing okay, doing well. We have a comparable performance to Whisper. By the way, I don't use a word like outperform or something like that, because training data is completely different. So it's difficult to compare. But I just want to say that it's comparable. And I also want to remark two things. One is that some of the English data we actually have a better performance than Whisper. And another is a little bit kind of the weird result. Wall Street Journal result is actually very bad. And I will explain why this happened. But why is important. So first, the OpenAI Whisper is over 400,000 hours for English, while the Awesome only has 73,000 hours. So in general, then the Awesome would be not be better than the Whisper, but actually some selected training data, some selected data, library speech, switchboard, and Tetrium, actually Awesome is better. Why? I don't know about the OpenAI's Whisper system, but at least ours, we actually including them, library speech, switchboard, Tetrium training set in our training data. Of course, test set we don't include, of course. But this means that we can actually creating a matched training data. This is the reason that Awesome is better than the Whisper in this particular part. But others, we cannot actually make it better than Whisper. This is purely based on the actually data volume or data mismatch issue. And the next one is Wall Street Journal result. Actually, the Wall Street Journal result is very kind of the mysterious. So from the version 2, the performance is okay, 3.7. And we move to the version 3, it goes to suddenly worse. And then actually, from version 2 to version 3, we include the Wall Street Journal training data. So if we follow the previous kind of logic, we must make this improve, right? However, we actually cannot make the Wall Street Journal to be better. This is actually later we actually debug it and found it. Think how many people, by the way, still touch Wall Street Journal training data? Maybe not so many people. There are some, okay. Then you guys can actually understand it, right? Wall Street Journal is very weird. Like, you know, they actually the speak double quote, I ask you, comma, or something like that. It's a little bit kind of a different style. The training data is actually quite a different style. And for me, and some of you also agree, almost like a different language, right? And then what's happening is that we include this one to training data. And then since the model is actually first recognize that Wall Street Journal recording condition, oh, this one is Wall Street Journal. And then we should output like this style of the text. So this is the reason that Wall Street Journal, we actually get the performance worse. This is format issue. But anyway, I want to mention that we can identify why the Awesome is sometimes good and sometimes bad based on this kind of the transparency of the data. So I would say that Awesome is more explainable than the Whisper at least. And I also want to mention that explainability is the most important part of the science. Okay, then now I kind of move to the functionality. So this part I will go quickly. So first, the timestamp prediction is working quite well. And then we actually get the almost similar the performance to the Whisper's timestamp. And second one, the long form recording is actually not very good. We actually found a reason because we're using a lot of training data came from the one sentence. And then we just padding to the 30 second, padding to the silence to make it 30 second. So this means that we actually don't have so many long sentences in our training data. This actually causes a kind of possible the degradation compared with Whisper. So this is also another issue in the data mismatch. However, we actually get a very good performance in some of the languages, like English, the Japanese, and Mandarin. This is also the similar the discussion as I mentioned, because we usually have a very good data for these three languages. So due to that, we can get a very good performance. And the prompting is working. And the next one is that I mentioned before. So Whisper, we throw the silence. They actually said thank you, right? And what's happening in the Awesome? I hope we want to improve the performance for this part. But unfortunately, he said that it's a good thing to do. This hallucination still exists. So this is a first generation of Awesome. We actually have a comparable result to some of the kind of selected cases. But we found other many issues, training cost, data volume, the format, hallucination. But now we know the issues, so it's time to improve it. So I will move to the how we kind of improve these models and so on. So we still have how many? It's
You have time. Yeah.
starting from the
You have like 15 minutes?
15 minutes. Okay, sounds good. Okay, so this sounds like a very trivial, but I just want to mention that this training is super expensive. So we want to kind of follow the kind of major scientific methodology, like identify the problem, using the technique to improve the performance, doing some experiments, and then publish the result. This kind of process is quite kind of difficult for the current the large foundation models. But in our kind of approaches, we try to stick to this kind of scientific methodology. And then based on the issues that I pointed out in the previous slide, now we try to kind of solve this problem one by one. So first part is format, mainly came from, turns out from the Wall Street Journal training data. How did we do that? We actually just exclude such kind of training data. But it's not only this. Given this kind of format issue, what we have done, is actually we revisit all kind of format issue and then de-normalize many of the text data. Second one, training cost. And then we actually introduced our kind of the latest work, the Awesome version 3.1, which we kind of submitted to the archive. So this was actually based on the experience we had. Yes, we did a lot of kind of massive experiments, and after we did it, we actually found a lot of ways to improve our training. We actually using the better architecture to make the convergence fast from the transformer. We also using the new learning rate the scheduler. And we also using the several latest techniques to efficiently train the model, especially flash attention. So now the training cost becomes first. So we actually continue this effort, again, not just for the making our training to be faster, but for the carbon footprint. And through this kind of a process, we also had a more experience and try to actually prepare several model sizes, like a small base and the medium, the awesome models. So this is actually the result that we had in the such kind of the effort. So original the awesome is here, and this is a kind of whisper. And then this is the awesome result. For this is a kind of average of the all English test set that I kind of showed before. And actually, after our kind of experience, we really kind of feel kind of the difficult to use a very massive computing resource in the first generation. But from the second generation, we can make it faster, not only for the training and the inference, and also making the performance better. We also found a very interesting emergent ability. So now this kind of emergent ability was discussed many in the large language models, right? We also actually found the emergent ability in speech. So this is a completely byproduct, by the way. We actually prepared a small, medium phase, and then we found this kind of a capability, which is zero-shot contextual biasing. So in the Whisper, as I said, or Awesome, we actually always train the model by inserting the previous text, okay, during training. But during inference, we actually insert some kind of a biasing keyword, and then we can actually correct the ASR result. This is called contextual biasing, which is very important technique because we cannot easily recognize named entity and so on. But we sometimes have the list in advance. And then we can using a contextual biasing. This is a big speech recognition research area now, and many people actually working on it. However, our actually approach is we didn't specifically train the model to do the contextual biasing, but we found that it's working. So I actually prepared a demonstration about it, although it's actually working. It's okay. So it's okay. This is not so much important result. What I did was that, sorry, I actually speak Shinji Watanabe is working on the working at CMU, and they actually recognize Shinji Watanabe. Sounds very weird. It's difficult for the ASR engine to recognize such kind of foreign name, right? I actually type here Shinji Watanabe. This is kind of we know the keyword list, and then we can type it, right? And then after that, we did doing the inference again, and actually will recognize Shinji Watanabe and so on. And again, this is a contextual biasing, a kind of typical example of the contextual biasing, which is obtained without I kind of ask them to train such kind of weights, just that the previous text is inserted during training. And this is actually the several the numbers that we show it. So this is the without biasing word and with bias word, and then small model, the most smallest model, actually doesn't improve the performance so much. But if we increase the model size, and then we actually suddenly get the better performance, which is a kind of one of the typical emergent capability of the big foundation models. If we want to play with the more, you can actually also play it in our demonstration pages. And the next one is hallucination. So why hallucination happens? This is actually especially happened in the encoder-decoder structure. These are kind of an okay case. In this case, attention pattern is clearly kind of try to connect the encoder and the decoder in the diagonal, the attention pattern, which is speech recognition cases, it is normally working. But when hallucination happens, it's actually attention doesn't connect to the encoder. And then decoder is just started to run away. And then some hallucination happens. I often using this cartoon. So encoder and the decoder is the dog. And if we don't have a lead, they may actually run away and may do some hallucination. But if we have a hard alignment, hard assignment, it doesn't happen, right? And there are a lot of ways to make it hard assignment. One way in speech recognition, well-known approach is why not we just use a CTC, connectionist temporal classification, or RNN transducer. By using this, actually model itself does not harbor the hallucination because decoder is very shallow and always the input and the output is connected with hard alignment. So hallucination doesn't happen in the model level. Of course, again, many people are working on the beam search level or anyway inference level, but by using this kind of the models, we actually avoid the hallucination. And this is the result. We call it the awesome CTC version. This actually completely removed hallucination that we had before in the awesome models. And then in these cases, just one hallucination we found, except for that for ASR task, we actually didn't get any other hallucination. By the way, again, this part is, now the very difficult part, even the whisper with a sophisticated decoding, we cannot completely eliminate the hallucination. But we understand the model and setting the model like this, we actually can avoid the hallucination. Okay, last part, data. This is still ongoing work. But anyway, the most difficult part is the amount of training data. They are three times larger than ours. Or they started to use the self-training, and then their actually training is now the 20 times larger. But we also tried to kind of follow this direction. We actually started to use the YouTube data, but we only use the Creative Commons portion. So we don't actually violate any kind of the license issue. And then we collected the data, and currently we have 300,000 hours with the YouTube data and the corresponding transcription and so on. It is very noisy, but it's actually at a quite large scale. So if you guys are interested in, please also touch this data. We are actually still working on making it more and clean this data and try to use it for the next generation of the awesome and so on. And in addition, we also are collecting the large amount of the unlabeled data. We are collecting the around 1 million data. Or again, that we kind of check the license of such kind of training data, and then we release this data to the public. This one actually covers over 4,000 languages. Finally, this is more like the recent kind of activity in our group. Given this direction, we should more focus on the fine tuning, the pre-training, kind of splitting the role. So we also starting another kind of open source project called ESPNet Easy. Easy comes from the easy. This is fully Pythonic. And the awesome or whisper or whatever, we just using the large pre-trained the foundation model, and then we actually supporting the multiple data set like ESPNet, PyTorch, Hugging Face, and the trainer also the several the trainer we are supporting. So that we can actually easily using the fine tuning of this kind of models. So we are still in the development stage. So if you are interested in working with us, please also let me know. Okay, so let me summarize my talk. So first, I think not only speech, many of the foundation models now makes us very kind of excited, right? However, there are several the points that we should be careful. So, like for example, explainability. This is a main main kind of theme in this workshop, and this is actually exactly very important problem. And also, make some effort to keep the our kind of the training the transparent. This is quite important. So if you are allowed to do that, let's try to do that. Actually, after this kind of the effort, I got a lot of feedback about it. Why I can get the feedback? Because I released all training data. People actually, for example, tell me, Shinji, you should use this data. Shinji, you should care about the bias if using this data and so on. I had a lot of feedback about it. And I'm very kind of excited that releasing all of this kind of information to the public. And finally, this is a take-home message. So I try to kind of careful about this word. I hope someone may not misunderstand my point. But anyway, as researchers, we should be responsible for what we have done for future generation. So it's good to work on the interest or some of the missions in your institutions and so on. But we should make it in your mind. And as I mentioned, that in this kind of awesome project, I found two kind of issue. One is a large training cost. This actually caused some carbon footprint. And also, without explainability, we will have a lot of issues. For example, again, unfortunately, some of the large models doesn't disclose various information. So if they disclose such information, we may not have to have a lot of effort, but due to this kind of issues, we actually have to analyze, investigate, probe such kind of models and so on. So this actually additionally kind of increase the carbon footprint. So even fine tuning, we should actually have the issue in the carbon footprint. And we also, without the explainability, we will lose the control, right? And which further damage in our Earth and humans and so on. So please remind that we, the researchers, had such kind of issue in the past, like pollutions and so on. But again, I fully understand some of the company's mission or some of your institution missions that cannot fully kind of making this part to be explainable and so on. So in this case, maybe some people in the academia or some of the companies that more flexible the policies should actually complement this kind of situations. Some companies, let's try to build more exciting models. And academia or some kind of flexible company, let's try to give them some more explainable other functions so that we can complement our society and advance that speech and audio technologies more. So that this is the last my message. Let's make an explainable speech foundation model together, not only with us, with you guys. Thank you so much.
Thank you very much, Shinji. So, questions? There's one. Yeah. Yes.
All right, Shinji, thanks for the talk. So, so in terms of building the awesome models, I wonder that. So when you guys are collecting the like piling the data, are you guys pile all the data in one shot, or like you just collect partially collect the data partially and train a model and see how it works, and then gradually increase the data?
Yes, good question. We actually gradually increasing. First version, we only using 40,000 hour. 40,000 is, by the way, very large for the academia. But we want to have some level of the large amount. So we starting from the 40,000 hours, including ASR and speech translation data, and then finished all the kind of a basic implementation. And then we found that our implementation is correct. And then we moved gradually from the 120,000 hours of training data, and then now 180,000 hours the training data. However, every time we start from scratch.
Okay, so you guys, that means that you have trained multiple variants of the awesome model. So one question then is that until because I personally did this experiments before that gradually increase the data on a different speech task. So until which point you guys begin to figure it out that the performance begins to be maybe saturated, or the performance begins to be as good as the original OpenAI Whisper at some point?
Maybe some point, but it's also depend on the data balance, data quality, and so on. So this is actually also through this project, I learned a lot. Yeah, it is very obvious, but the data distribution is very different depending on our kind of tasks and so on. Again, I don't know about Whisper, so they actually disclose some information, but I exactly don't know what kind of data they are using. But in our project, we actually try to use the public data as much as possible. So this means that many of the portion of the training data is red speech, came from English or other languages, audiobook. So that some of the tasks, the hours are very good, but the conversational speech, actually the hours are behind in the Whisper. And then how to do that? Again, as I mentioned, my kind of some of the future or ongoing work, we started to collect the YouTube data, Yoda's data, and so on. By the way, again, this is the YouTube actually has two licenses. One is the YouTube, their own license, and the other is Creative Commons for the creators and so on. So we only using this creator common part so that we could expand it, and also we fully publicly release this data so that community can also reproduce the same training data. By the way, one more comment. People here, let's try to upload YouTube data with a Creative Commons, including this talk, Jem, so that we can increase the training data more for this kind of project. Yes, so we understand that there's some kind of the issues in the data distribution, and it is not simply like just increasing it. So yes, sorry that it's not a fully kind of answer of your question, but we learned a lot that just fully increase the amount of training data is not enough. We should care about the distribution. We should also sometimes using some of the technique like upsampling and so on to make the model to be unbiased to the specific conditions.
A final question is that when you guys compare the Whisper model, you started from obviously English SR and they expanded to multiple tasks. So but obviously the original Whisper also has the ability to act as other self-supervised learning models by extracting embedding, and which can be used as features for other tasks. So how about Awesome? Do we have any plans to, or have we already done extracting, making it like a SSL model which we can extract feature from and have multiple and expand it to multiple downstream tasks?
Very good question. Actually, this is a way to actually using more wider data, right? Yes, we are actually working on it. We are have several ongoing work of making a SSL model and then using it as a kind of a pre-training or a feature to the awesome model. Yes, we have such kind of project exist. And I just want to make sure that the Whisper doesn't use SSL model. They just using the self-training. After they have a kind of large model, they actually are using the pseudo labeling and then extend to the million the hours of training data and so on. We are currently focusing on the SSL-based approaches, but we may also think about this pseudo labeling approaches. So this is still more in the research stage.
Hello, Dr. Watanabe. Thank you very much for the awesome talk.
Thank you.
Pun intended. Yeah. So this is a bit of a meta question, I guess. So like you mentioned a lot about the reproducibility issue, like especially let's say with our work here in ICAS, if we could change one thing about ICAS submission to make the submission process to make all of the models here more reproducible, what do you think would be the one change that you would make? Yeah.
Yeah, that's a kind of great point, right? And actually several other the conferences the having such kind of structure, right? And again, but at the same time, my talk again, the reproducibility is important, but there are several other factors that is more more important for some of the institutions. So probably this part may not be just more like not to be like a mandatory, but more like recommendation suggestions. But definitely we should have even in the kind of the submission protocol to for people to more respect the reproducibility. I think this is a good idea. Yeah.
Hi, thank you very much for the talk. Just one question regarding the hallucinations and disconnection from encoder decoder part. I wanted to know first, is it something that is measurable or you just detect it? And also I wanted to know if, have you tried to see if it is affected by pauses or silences in the speech?
Very good question. Yes, that we have some measure. First, we usually checking the attention rate. And then if this is a kind of not expected pattern, then we could actually find that can be the hallucinated and so on. By the way, this can be done not just analysis, but during the beam search and so on. So there are a lot of approaches to just checking the attention pattern or some kind of the frequency of the same kind of n-gram, the counts, and then avoiding the hallucination, but by making a big penalty for the unnatural the n-gram counts or unnatural the attention patterns and so on. So we can actually doing that, we can avoid the hallucination to some extent. However, CTC and RN transducer, they are actually hard alignment based approaches. All kind of speech features are somehow they connected to the output token. And then we actually cannot hover the ways to without speech feature to generate some text so much. So our kind of solution is given this kind of analysis finding, just try to use the well-known ASR techniques to avoid the hallucination. By the way, one more comment about this part. Yeah, sorry about that. The whisper also had a speech translation, right? CTC speech translation sounds weird for some people because CTC actually assuming the monotonic alignment, but it turns out it's working. What's happening is that during the self-attention, reordering is happening. And after the encoder, already reorder is finished. And then after the final output, we just using a monotonic alignment. Still, we can get to the reorder, the speech translation result. So actually, speech translation result in the awesome CTC is also working very well.
Yeah, that's interesting part. Just about the attention, do you look at the self-attention, cross-attention?
Cross-attention, yeah, of course, cross-attention.
Yeah,
yes.
yeah, of course. Yeah. Thank you very much.
All right, we are over time. Thank you very much for your questions. Yeah, we are over time. Please take it offline. Thank you very much, Shinji.
Thank you.
So we will continue with a poster session, and then at 4 p.m. we'll have one more quicker talk, and then we will have the panel discussion.